Okay, good morning. I'm giving 4 modules on thermodynamics, and the way I have organized these is as follows here. Module 1, which is today, tomorrow, and day after. We will look at some applications and start looking at concepts and definitions. So it is today and day after tomorrow, we will complete these. After that, we'll come back after a few days and have a second set of 6 hours where we look at the laws of thermodynamics and various forms in which they get applied. The third module will look at properties of a pure substance and how we can get data from the laws and the concepts that we've got. And the final session, the 6 hours, will be on systematic problem solving. Okay, so we'll start today with concepts and definitions, but the first thing we will do is try to figure out and look at some applications as to why we should be studying a subject like this, or for that matter, why is thermodynamics important. Okay, so we'll look at one of the biggest problems that society faces today, and that is climate change. Just a few days back, all the heads of states of all the countries met in Paris to discuss and come up with a plan of what we need to do to combat climate change. And the organization that has been spearheading this activity is the IPCC, Intergovernmental Panel on Climate Change. And these are a series of reports that they have produced starting from 1990 and coming now and saying that in the 5th report, what are the issues and what is the importance of climate change. Okay, so what is climate? This is basically accumulation of carbon dioxide in the atmosphere, which traps heat from being radiated out, and so the average temperature of the atmosphere keeps increasing. Nature itself does a lot of things with both carbon dioxide, methane, and CFCs. And this picture shows in a very crisp way what are the big items in the carbons. There's atmospheric growth, land use change, that means forests get converted into agricultural land by burning, land sinks, lands absorb carbon dioxide, and ocean sinks, ocean absorbs carbon dioxide. But you see this first column on the left, first item on the left side, this is fossil fuel and cement, and this is the biggest item that results in permanent carbon dioxide addition to the atmosphere. And when we say permanent, it means that we are excluding natural phenomena like, say, a volcano going off. So how did this thing become so important, whose effects we are now actually seeing all around us? This graph shows us a historical trending from 1800, we are down to 2000. This graph can now be extrapolated another 15 years. And it tells you what is the total amount of global fossil carbon emissions in million metric tons of carbon per year. And you can see the graph for until 1850, and there is historical data that even before this, CO2 was not going up at any rate like that. Then it slowly started going up, and something around 1950 onwards, there's been a spike, and it's going up quite rapidly. So, and where did this permanent addition of carbon come from? You can see here, this line there is coal. Until 1900, or predominantly coal that was responsible for permanent carbon addition to the atmosphere. For early 1900s onwards, petroleum started coming in, and now petroleum and coal are about of comparable magnitude. And then much later, about 50 years back, natural gas started coming in, and cement is still a very small amount. So it's not really a big issue for us. But here is consumption of natural gas, consumption of petroleum, which is oils, and consumption of coal. The question is who and why and how do we consume these things? And are we also in this? Before you get to that, here's some evidence from how carbon dioxide concentration in the atmosphere has changed. And this is this line here. 1880 onward, it was about 290 parts per million. In 2000, it had reached close to 375 parts per million. And we know now that last year, CO2 concentration in the atmosphere hit 400 parts per million. This looks like a very, very small number. So why should we worry about such a small number? but its impact on climate change is substantial. And that is what is the whole worry all about. And there is now increasingly agreement in the scientific community that climate change is for real. Events around us that are happening every day can in some way be attributed or are aggravated by climate change. And this is the reason behind this is the increase in the average atmospheric temperature. And this is what this graph shows here. It goes up and down, and this is the average temperature of the atmosphere, and it's the change in average temperature of the atmosphere in degrees Fahrenheit. So to get to degrees Celsius, you can just approximately half these. So it shows that this graph is pretty zigzag type of a thing. And one has to go into a lot of statistical and computational techniques to say, how do I calculate the average temperature of the atmosphere when at any given time, somewhere in the atmosphere it is minus 60 degrees Celsius, and somewhere else it could be plus 50 degrees Celsius, and it's changing all the time. There have been methods, a lot of research has been done on this, and now people agree that, okay, this is the way we should calculate the average temperature of the Earth. And yes, it does go up and down, but then what one does is look at something called trending. And that tells you that pre-1940 or maybe even 1950, temperatures were a little bit less than the average there. And in the last 50 years, there has been a substantial increase. Increase means it's just about 1 degree Fahrenheit, that's half a degree Celsius in rise in the average temperature of the atmosphere. This may again look like a very, very small number, and one can always argue that when there are such wide variations in the temperature across the planet, how can you even talk about an average temperature like that? But all those discussions and debates happened about 25 years back, and scientific community is now pretty much convinced that this is for real, and the ifs and buts on this are pretty much settled. So we have been adding carbon dioxide to the atmosphere, and what are the impacts of that? Here we have three graphs. The first one shows the global average surface temperature, and this comes about a little bit more than 2000, and it shows that with base as 1960, the temperatures which were half a degree Celsius below that prior to that are now about half a degree Celsius more than that. And implications of that: global average mean sea level. One of the first things that people are worried about is that because of heating, it's like a mercury thermometer. The water will get heated up, it will expand, and the mean sea level will rise. And that is what this graph shows. It shows that between about 1870 and now, mean sea levels have increased by about 300 millimeters, 400 millimeters, somewhere in that range. That may be a small number, but this trend is what is really worrying. You can see that this is a very clear trend that the mean sea level is going up. And in the last 15 years, again, this has gone up further. This has got tremendous implications for people all across the world, because 70% of the world's population lives along coastlines, and they depend on the sea for their survival. And many low-lying areas are already facing the prospect of submergence. Maldives is the first nation which may actually go underwater. Our neighboring country, Bangladesh, very large section of the land is already gone underwater, and if sea level continues to rise this way, an increase in about a meter in mean sea level, about a third of Bangladesh will go underwater. This will be a huge human tragedy. The other thing that people are worried about is the snow cover. This is the region which is most sensitive to change in the temperature of the atmosphere. So the Arctic pole, the Antarctic pole, and there's a lot of data on that. But what I presented here is northern hemisphere snow cover, which is the large chunk of it beyond the poles is the Himalayas. The Himalayan glaciers are probably the biggest chunk of ice, inventory of ice beyond the North and the Arctic and the Antarctic. And there is enough evidence to show that the area of snow cover has been decreasing. One only has to travel to Himachal or Uttarakhand or Kashmir or anywhere else in the Himalayas to recognize that what was snow covered until about say 20 years ago, that snow has disappeared now. The glaciers have shrunk by several kilometers. And this is very alarming because all the Himalayan rivers on which we depend on so heavily. So let's see, where does the permanent CO2 to the atmosphere come from? So we are seeing here is a graph from 1971 to 2013, world CO2 emissions from fuel combustion. This is coal, there is oil and natural gas. Coal is clearly the biggest chunk up there. Then comes oil, and then there is gas. And so we ask now the question, who is burning this coal, why, how, and how do we benefit from it? So there is burning of fossil fuel. This has resulted in CO2 into the atmosphere, and now we see what is it that this comes from. Coal, then there is oil or petroleum, and gas, natural gas. Coal, well over 90% of this is used for generating electricity. And that's where even in our country, about 80% of our electricity comes by burning coal. Similar is the story with China, same with Russia and the US. So that's the extent to which very large number of people actually depend on coal, the burning of coal, to get electricity. And this is very important because we think that electricity is a very basic necessity of life, and it in many ways defines how well we live. Oil, a large fraction of that oil, about 50% plus, and that varies from country to country, is used in transport, car, road transport, somewhat less on rail transport, and increasingly air transport. Natural gas similarly is used for power generation, but some other direct heating purposes also. Oils are also used in very large quantities in industries. Any industry that needs steel or needs to heat, one would use oil. Say a forging manufacturer, they need to heat billets of steel. So you have a furnace in which you burn oil, put the steel in it, becomes hot, take it out, forge it, and make the component. Natural gas also goes for fertilizers, but that's one of the big things. And in our country, it's still a much smaller amount for transport. So this is the overall picture, that we get almost 80% of our electricity, 90% of our electricity from coal. So if you look at the reverse matrix, where does the electricity come from? Well, 80+% is by burning coal, and then the rest comes about 15% from hydroelectric power plants, and then 5% and increasing slightly from all other sources, especially like renewables, like wind, solar, and so on. So what we are seeing is that CO2 got generated because we wanted electricity and transport and many other good things of life. And in the process, we are all adding a small amount of carbon dioxide to the atmosphere. Okay, so now we look at the second part. Where do we use electricity? It varies again from country to country. We'll take numbers for our country, get approximate feel for what it's like. A couple of percent of this is used for rail transport. If you have seen electric locomotives, remember that loco looks quite nice, it's not throwing out any smoke, but it got its electricity, and that came, most of it, from coal burning. Then there's agriculture. depending on the season, anything like from 30 to 50% of the electricity, depending on which state and which region we are looking at, could be going to agriculture. In off season, it could be less. The monsoon is good, this number comes down. Then there is defense. We do not have exact numbers, but very many things that are there, especially in the storage of ammunition, critically depend on the availability of electricity. Then we have domestic consumption, and last is industry. Industry critically depends on reliable electricity supply. And to remain in business, if the power supply keeps going off and on, it is quite disastrous for industry, and quite often they and many others start installing or sometimes completely using a diesel generator set. It's a diesel engine coupled to a generator, and you buy diesel oil, burn it and use it. If you have seen at homes or even in your institutions, if the electricity goes off, you have a backup diesel generator on campus and like that. So what has happened is, because our electric system was not very reliable, many people started putting up DG sets, and though these are small in size, they are very large in number, and today the total capacity of generating electricity from DG sets is comparable to that we have from coal burning thermal power stations. So that's a huge amount of investment and also continuing diesel consumption that happens just to keep things going. Within, say, domestic and say we can even put here commercial sector, the situation varies from place to place, but if you take an urban area, say like Delhi, then the ambient temperature drives the electric power consumption. If there is a shower and things cool down, power consumption goes down. It becomes hot and humid, power consumption goes up. And the reason this happens is air conditioning. And this is the single biggest reason for increase in the share of domestic electric power consumption in the total sector. Okay, so this is a quick scenario of what we have around us. And let's see where does thermodynamics come in. First, let's look from the usage side. The analysis of diesel generator sets we understand from this course. Air conditioners, refrigerators, this is an application that we will look at in this course. And when it comes to generation, this is entirely the domain of thermodynamics. Automotive transport sector also, indirectly industry is also, natural gas, electric power and transportation, this is also covered. So you see that thermodynamics is in some way connected in a very big way to the consumption of fossil fuels and in the end consumption of electricity. So now let's see the real world, and do we see something on that? Okay, so this is in Google Maps, and this is our campus here. This is our main building. I am standing somewhere in this, and let's see what's around us here. Okay, here this is the Yamuna River, and we see this patch here, black stuff. So let's see what this is. So what is coming into view is this big thing, which is a black thing, which is the storage of coal, and this is the Badarpur thermal power station of NTPC. Okay, so here we see one chimney there, and this whole thing you see here is smoke coming out of this thermal power plant. And this of course includes carbon dioxide, but then there are some ash particles in it and some amounts of nitrous oxide, sulfur oxide and all of that. And what you see here, this rectangular thing here is a boiler into which we continuously feed coal, burn it. We also simultaneously pump oil through tubes which get heated by this fire generated by the coal, and we produce high pressure, high temperature steam, which is then led through pipes into this building, inside which there is a steam turbine coupled to an electric generator, and that's how we get electricity in further out here into the switch yard and then into the transmission system and all the way to the users. So what you see here is one boiler. We do not see the turbine here. We'll in a minute see some pictures on that. These things that you see are the exhaust gases coming out of the boiler. It goes into these two things and then also into these. So this is a cleaning system called electrostatic precipitator, which removes a lot of the ash from this gas. And then finally it is led into the bottom of the chimney and it goes off. So this is one power station, and that gives electricity to Delhi. It's a fairly old one, about 40 years old, and in the process of being shut down now. And this is being replaced by new power stations. And one of the relatively new power stations is at Dadri. It's about 80 kilometers from Delhi. And this is the entire area on which the power station is placed. And so let's see what do we see here. Yeah. So to understand what this whole thing is all about, bottom line is that it is supplying electricity to the northern grid, about 3000 megawatts. And like the other power station we saw a few minutes back, here we have these square things of them. These are 4 independent boilers. These are the electrostatic precipitators, and the gas from all of them is led into this big thing, of which you see 4 openings. There are 4 chimneys of the 4 boilers out here. Very light smoke you can see coming out from this. So some of these are operating. It is in this building that the generators and the turbines are kept. From there the electricity comes out. So these are 4 units, each generating 210 megawatts. Not generating, but capable of generating 210,000 kilowatts. Next to that are again 2 structures here with 1 chimney. You can see 2 openings up at the top. These are relatively new boilers, just about 4 or 5 years back. Each one capable of generating almost 500 megawatts. Again, they burn coal, and so that is one old power plant. This is a new one, and again it has got its own substation and everything else. On the same space, we see here something else, and this is a combined cycle power plant. This can burn gas or naphtha, and what you have here is inside this building over here is a gas turbine where we burn gas and generate electricity, and then the hot gases come into this device here where this energy is given to water which produces steam, and that is again led back into this building, and there is a steam turbine which generates electricity, and then the gases are thrown out. So a little more complicated system, but environmentally more friendly. You are not burning coal, and also its efficiency, the thermodynamic efficiency, is greater than that of a coal burning power plant. So you can see there are 2 steams there. So there are 2 gas turbines, and in between there is 1 steam turbine, and the same arrangement is repeated in this part of the power station. A little further down is this facility here. These 2 are very tall buildings, and what they do is through this transmission system they receive electricity generated about 800 kilometers away at Rihand Super Thermal Power Station. It is converted into DC power, and straight away from there it comes here, and through solid state systems this 1500 megawatts of electricity is converted back into AC power into this switchyard and then added to the northern grid. So we now have such systems where if you want to transmit electricity over long distances, we use this technique called HVDC transmission, high voltage DC transmission, and one of the biggest lines recent now that is operating is from Talcher in Odisha. The electricity is sent directly to Bangalore. So these are some, this tells us what the actual machine, what will I see. First, we look at the picture of a coal burning power plant. So these tall things are the boilers, and this is NTPC Korba, and you can see how many chimneys and how many generators are there. In this whole area, there are many more generating stations, and this is the so-called the power capital of India. So there's a huge amount of coal mining taking place, and all that coal is also being burned, smoke and carbon dioxide. Let's go inside the power station and see what happens. Okay, so this is a picture not from an Indian power plant, but which till date is the largest steam turbine generator in the world. It has got two streams here. What you see on this side from here to that other end, this is the steam turbine, this is the generator. And so like that there is a second arrangement that side and a second generator here, each of these producing 650 megawatts. So it can total generate 1300 megawatts. Again, this is a coal burning power plant, and what you see here are just lots of big structures, pipes. These are pipes. You now see another picture and looks very clean, and you can get an idea how big it is. There's a person walking over there. These are all steam turbines in which steam is coming from these pipes, going in and exhausting from below and condensing it. And all of these are rotating a shaft which is connected to a rotor of this generator, and that is producing electricity and sending it out. This is a nuclear power plant. And so, except for the nuclear reactor, where there's a very different phenomena taking place, rest of it, the analysis comes from thermodynamics. Whether it's a breeder reactor, whether it's a thermal reactor, or whatever type of nuclear power plant. And what you saw in those pictures as big, just boxes, and you couldn't see anything. In fact, if you stand near it, you won't see anything moving probably. You'll hear a lot of noise and feel some heat. But when it is being manufactured and assembled, this is what it looks like. These are forged steel components. This is a rotor on which these things are put, which is blades. And like this, each of these things is called a stage. And like this, you got lots of these stages which are fixed onto the rotor. So each blade is made separately, the rotor is made separately, they are all assembled together in the factory, and then it is sent off to the site where this casing, which you see the housing here, this has been machined in the factory, it is installed, and then the rotor is put in it, and finally the upper cover is put in it, and then it is all bolted together. These are holes for bolts, and you have a steam turbine. It's a very, very sophisticated machine. That is one application of thermodynamics. Coal or oil burning, combined cycle power plants. And we now look at something else. There is a lot of talk now about solar energy, and there are many places in India where installing solar photovoltaic cells for generating electricity, and that we hope we will reduce our dependence on coal and oil and gas, and that will become a little more eco-friendly system. So this is a very recent, less than 5 years back, this power plant was completed, and this is in Spain. This is the concentrating solar plant, and what it does is that there are two plants here. This is one plant and this is another plant. This tower here, you see a little bit shiny thing here. Inside this, one is pumping water and converting it into steam, and that steam is led into this system where it drives the turbine, like the turbine pictures I showed you just now. It is condensed and put back in here. But the heating of the water to steam, instead of being done by burning coal or oil or by heat from a nuclear reactor, is being done by focusing solar energy through all these little mirrors here into this point and generating electricity, heating up the water. So you can see the huge amount of area that is required. Each one of these is what is called a heliostat, and all it does is that it reflects the sunlight directly into this spot, and that gets heated up. This power plant achieved a unique distinction in that this will work only when the sun is up. And as from morning till evening the sun energy goes up and down, it means that you have to start and shut down this plant, and at night you cannot produce any electricity. Then what do? Well, go back to burning coal. So can we store this energy? So this plant used a very large storage system. So during the day, it had enough heat that some of it was used to produce steam and run the turbines, and some more energy with which a material was heated up, and then at night or when the sun went down, energy was taken from that storage and then electricity was produced from that. So this is the first solar thermal power plant in the world that produced electricity continuously on a 24-hour basis without resorting to coal or oil or any other backup. This distance is of the order of a kilometer or 2 kilometers. Many of these are there, and this is one of the designs of a solar thermal power plant. The second type of a solar thermal power plant is, you can see in this picture now, this is called a parabolic trough collector. And what you are seeing here is a little parabola, and you can see the distance goes several hundred meters, and they are all focusing sunlight into this little tube in the center which is supported above it, through which water or steam is being pumped. And to get a sizable amount of steam being produced, the length of these are long, so there is one here, one beyond that, something more there, and then there are many such rows, and they are all in a straight line, and you are aligning these with the sun as the sun goes from morning till evening. The sunlight is focused onto this outside of the tube. It heats up the water inside it, and that water is then connected through all these, you can see these shiny things. These are steam pipes which have been insulated, and on top of that there is aluminium cladding. So these are all the pipings that have been done here. You can see that here. And this steam is then taken to drive steam turbines. One can also take this steam to do, say, process heating, like, say, pasteurization of milk, or using it, say, in the manufacture of paper, or using it for, say, in a hotel for cooking, or in a base kitchen for, say, cooking and washing things. So those are the options that you have with this. And yet another option that we have with this steam is to use it in a vapor absorption system to produce a refrigeration effect. So this is the second type of a solar collector, and this is called solar thermal power generation, and this is different from solar photovoltaics because there you do not produce any steam. It is directly converting sunlight into electricity. So we'll leave solar steam generation and look at another different application in which thermodynamics can help us see what happens. And that is a fairly old technology, very simple thing. This is called a solar still. All it does is, you made a chamber there, the glass pane on the top facing the sunlight, salt water, dirty water is put here, and it flows down this side, and because of heat, the liquid vaporizes. The glass pane is cooler, so it condenses on the glass pane, flows along the glass pane, gets collected here and comes out. The result is, from dirty water, using solar energy to get clean drinking water. So this has been an idea that's been there and it's been developed quite a lot. There are many configurations of this. We'll now look at another type of a desalination plant, and this photograph is from Kavaratti Island in the Lakshadweep. These are remote islands where getting anything is very difficult. It has got to come from the west coast, and one of the biggest problems facing the people in the islands was clean drinking water. They are all surrounded by ocean full of salty water, and so this technology was developed at NIOT in Chennai, and this is called low temperature thermal desalination. This is the building in which the desalination takes place, and you get clean drinking water coming in. In the last few years, such plants have been set up in Minicoy and a couple of other islands in the Lakshadweep, and because of that, waterborne diseases have been largely eliminated from those islands. How do we analyze it? How does it work? That is where thermodynamics can help us see it. Basically, what you are doing is you take warm water and vaporize it and condense it at a lower temperature. The warm water comes from the upper part of the sea. The cold water comes from 350 meters below the sea. And use those two sources of heat to produce clean drinking water. Okay, now we'll look at another application, and this is aircraft engines. Okay, this is a slide I am taken from the web. This is not my stuff, and it gives a overview of how engine technology has been changing. In a minute, I will show you some pictures of engines. Year 1940, the first engines were invented there by Whittle in the UK, and then we are now at here 2015, and these are different model numbers of engines that have been made. So what one sees is that engines which were the first few engines were very small. The thrust they produced was not even 10, of the order of 10 kilopound force. And these are, the squares denote military engines for fighter aircraft, and these denote engines for civilian aircraft. And you can see these engines getting bigger and bigger and bigger every few years. And now from where it was like 10, we are now looking at engines in this range, which are of the order of 120 kilopounds per force. Engines have become huge. They have not just become huge, and these are the names of different manufacturers over there. R.R. Trent is Rolls-Royce Trent engine, which is used in the Airbus 380 and Boeing 787. And the other competitors are PW, Pratt & Whitney, and GE, General Electric. So these are the three companies that make big aircraft engines in the world now. What you see here is a plot which shows year-wise what is the thrust to weight ratio. So for the same weight of the engine, how much thrust do I get? And you can see that what it was like 1 in whatever units was there. This is there. Today's engines are about 7 times more efficient than what they were when the first engines were made, so even in the 50s. So it's a huge development that has taken place. And specific fuel consumption. How much fuel does the engine consume to lift a particular weight or fly a person a particular distance? And here it is that the first engines, which were like about 1 or little more than 1 pound per hour per pound force, today we are looking at engines which are of the order of like 0.4. So in about 40 years, the efficiency has increased more than 4 times. That trend, as you can see, is going on, and people predict that this trend will still continue for the next maybe 20 years. You'll see more and more efficient engines coming in. This is where the thermodynamics really gets you to understand why and how things happen. Thermodynamics, what is telling you that air is here, and what is the maximum temperature in that turbine. So in the turbine, you have taken air, compressed it, and then one burns fuel in it, typically oil. So the maximum temperature of that oil is a direct relation to what is the efficiency of this machine. And here is what has happened. If you look at, these are military engines here, the square ones, their efficiencies, their inlet temperatures have gone much faster and much higher. And civilian engines are over here. You can see all these spots going up. And what one sees is that the turbine inlet temperatures, say, which were in 1970s, were of the order of about, this side is about 1600 Kelvin. So that's about, say, 1300 degrees Celsius or 1200 degrees Celsius. Today, engines have of the order of 2000 Kelvin or 2000 Kelvin, which is about 1700 degrees Celsius temperature of the gas. Just compare that with the fact that the melting point of steel is about 1500 degrees Celsius. So what you have done is enormous amount of research and development, where you are now actually putting a gas over a material. So the gas temperature is more than the melting point of that material. And that is where advances have taken place in manufacturing, in materials. So there were, you can see here, these were conventional engines. Then various cooling technologies came about in this part. Then directional solidification techniques came in casting. and now you have composite materials coming in with a lot of ceramics in it. So this is how people are doing research on this, because thermodynamics tells you that higher temperature means higher efficiency. The second parameter that will come up in thermodynamics is the pressure ratio. What is the maximum pressure we generate? And here again you can see that over the last 40 years, pressures in engines have kept on increasing. So temperatures have increased, pressures have increased, aeroplanes have become much more efficient than what they were earlier. What does it mean for an airline? So this is a paper. I'm just going to show you one picture from this. So here is a picture which tells you on the x-axis is the year in which that particular engine was introduced, or the aeroplane was introduced. So aeroplane means aeroplane plus the engine. And on this side, energy intensity, which is how many megajoules did one consume for every revenue passenger kilometer. So every ticket paying passenger, if it was flown 1 kilometer, that is 1 revenue passenger kilometer. And here is what you see. The older engines, which were like Boeing 707, they were something like in this range, 4 to 6 on this scale. And we keep on seeing as we go along in time, DC-9, L-1011, Airbus 310, you still see that in India many places. Then you have Airbus 320, most airlines in India are flying this, or the Boeing 737, it will be somewhere on this picture here, that's Boeing 737. And then there is Boeing 777, and then here Airbus 380 and Boeing 787. What you are seeing is that these two aircraft are of the order of 1.5, which means they are about 3 times more energy efficient than a Boeing 707, or even if you take an aeroplane from the 1980s, say Airbus 310 or a Boeing 747 from that time, it is still at least 3 times more efficient or 2 times more efficient than a 20-year-old aeroplane. And this is a graph that shown what is the fleet average of the entire US. So airlines have consistently selling off older aeroplanes and buying newer aeroplanes, and that way they are reducing their fuel bill, which is the single biggest item in the cost of an airline ticket. And so an airline which continuously gets new aeroplanes and uses them for 3 years and sells them off, versus an airline which keeps an aeroplane flying for 15 years, that 15-year-old aeroplane and that airline will never be able to make a profit in today's world. And that's what you see happening with Air India. The average fleet age is way high, and newer airlines, the average fleets, they are still maintaining very, very low. So the fuel bill is less, and that's how airline tickets still have come down and down to a point where sometimes they can even start matching railway tickets. All of this has to do with thermodynamics, and that's what we will see in this course. So I'll just show a picture of an aircraft engine and then we will move on. I've already pasted it on the handout that I've given out. Okay, so here there is a aircraft engine. This is from Rolls-Royce Trent 700. It looks very, very complicated, and it is a very, very high-tech machine, extremely reliable, and there are lots of moving parts in it, but the essence is that there is a fan here which blows air and that generates the thrust. Some of the air else goes in through this and it gets compressed, and then there is fuel being burnt in this. It goes over these wheels and these to produce, these are the turbines, and the hot gases exhaust from there. So that's a typical construction of an aircraft engine, and you can see here there are pipes, there are tubes, there are sensors, and a lot of things that make this aircraft, this machine very, very reliable. But at the heart of this lies in the fact that there is something happening in this which has its basis in thermodynamics. So with that, let's say, but how do we begin to understand these types of systems?